Yeah, thank you for the invitation to come here, and thank you also for coming on the last day after lunch, which is very impressive. Because it's the last day and after lunch, I want this talk to be interactive, so please, if there's any questions that come up, obviously, let me know, and I'll do my best to answer. Okay, so this is a causality talk, so there is some similarity to what Stephanie was presenting earlier today, where you're looking at basically determining the effect of some kind of treatment. Now, in order to give some notation and to show some graphical terminology, I'm going to just give a toy example here, and then I'm going to break it in an interesting way. Okay, so what I've got here is it's a medical scenario. So I've got a disease that's being treated at hospital, and it has a mild or severe form. So X is the severity of the disease, can be mild or can be severe. Now, the doctor observes the severity, and then they decide on a course of treatment, which is either pills or surgery. It's more likely if the disease is mild that they'll be assigned pills, more likely if the disease is severe, they'll get assigned surgery. And then following both the severity and the treatment, you get an outcome, right, which is the patient is cured or not cured. And we have the following statistics in this toy example, so this is synthetic. Probability of being cured given pills is 0.85, probability of being cured given surgery is 0.72. So where do these come from? Well, they come from this expression up here. So the mean of y given a, and it's worth breaking this down. So basically, let's say that we've observed that we've got pills. Well, it's more likely that it's a mild form of the disease and less likely it's severe. So this weighting here takes the conditional mean of y given ax and gives more weight to the mild form, less to the severe form. Okay, and conversely, if I had surgery, it's more likely it's severe. So I take the mean of y given ax and I give more weight to severe and less to mild. Okay, so now that's our observed data. Let's look at our intervened data. So let's say that an administrator sees these numbers and say that pills are cheap and they work better, so everyone gets pills. That's what is happening on this graph here. So in this case, you've got an intervention which has a double boundary around it in my notation. This is my potential outcome, so this is y under the intervention A. And this is a sort of a situation where everybody gets pills. So I've got my chance of being cured, given treatment and severity, but I just average this now over my population because everyone's getting pills, so this is my average causal effect. And in this interventional distribution, obviously you get a lower rate of cure for pills because you're giving pills to people with severe form and it's not curing them. Okay, so this is to distinguish observation and intervention. So now let's make things more interesting. Let's say that in our hospital, our doctors don't record all of the details of the disease that they're observing, right? But they just instead record partial information. So in this case, they record whether the patient has a fever or not. Okay, that's all that they record. But the fever is highly correlated with this X. Okay, so probability of fever given mild is 0.2, fever given severe is 0.8. So it's not a perfect link, but it's a pretty close link. Okay, so let's say that we don't observe X. And a question might then be, well, can we find the effect of an intervention on A when all that we observe is W and not X, right? And in particular, if we wrote something like this down here, right, would this be enough, right? I'm taking y given A and W, and I'm marginalizing it over W. Well, as with all rhetorical questions, the answer is no. So here, the numbers that we get when we do this are in fact quite different. And in fact, because of the way that this has been set up, I flipped the ordering. And so, in fact, I'm giving more, let's say, probability of being cured to pills, when in fact the real number should be quite a bit lower. Okay? So obviously, as the connection between W and X gets less and less noisy, it reverts to the original setting. But in this not too noisy setting, I'm already in a lot of trouble. And in fact, it's been proved that unless you can sort of get this, P of W given X matrix on training data from observation, that you're not able, like it's undetermined, to find the causal effect, without having observed X, basically. Okay. So this then leads to a question, which is that, if we have some incomplete noisy information of X, is there a way of determining the causal effect? Now, we're going to see that the answer is yes, but we're going to need a little bit more information. And I'm going to describe in this talk exactly how much more information we need in order to recover the causal effect. Okay, so the next slide is our rules. So we need some rules, and some of these rules are common to the earlier talk today. so they'll already be familiar with you. So the first is the stable unit treatment value assumption, so no interference. So that means that the pill that I take doesn't cure the person next to me. Conditional exchangeability, what that basically amounts to saying is that I don't have some sort of V up here, which I don't get to see or account for, that is influencing A and Y. So this isn't allowed, or I'm assuming that this doesn't exist. So there's only sort of one X that I'm accounting for, which influences A and Y. And then overlap is basically saying I'm not going to draw any conclusions about things I've never seen. So if I never gave pills to someone with a severe form, what would happen if I gave them pills? Well, I don't know, I never tried it, okay? So that's sort of amounting to saying that everything that I'm making conclusions about are things that I have to have seen in the training data. All right. So we are going to do causal effect estimation with hidden covariates. We are going to do it using some noisy incomplete information, or some noisy information, I should say, about this hidden X. And this noisy information is going to be called a proxy variable. Okay, so I will introduce exactly what I mean by this in the talk. Now, there are many applications in which we don't get a complete view of some relevant hidden covariate, which the people in the training data have access to. So one might be privacy constraints. So I'm acting with a complete view of my data, but I'm only going to share some anonymized view of my own data to like a large internet company, let's say, okay? Another, which is an interesting case, is like a fundamental limitation. So let's say that I'm, based on my state of mind, I'm taking some action. Well, the observer can't know my state of mind, but maybe they can find noisy information about my state of mind by quizzes, by looking at my behavior. This is sort of a way of saying, look, I know my context, but an outside observer only has a noisy view of my context. Okay. What is new in this talk? So in this talk, but treatments, classically speaking, have been binary. You do something or you don't. In the presentation that I will give, treatments can be something much more complicated. So a treatment can be an exercise program or a radiotherapy regime or a piece of text, or it can be something very high dimensional. So my treatment is a high dimensional object. And my proxy variables, so my noisy observations of my hidden data, these are also high dimensional objects. And I'm going to give examples of that a little bit later. So all of these, treatment, proxy variables, etc., can be multivariate and complicated. In order to deal with multivariate complicated data, in this talk we're going to be using adaptive neural nets, and I'm going to describe how. We can also use kernel methods, but that's not going to be in this talk. A final, part of the manifesto is that we have what look like hidden variables here, like X is a hidden variable. I am going to claim that you shouldn't model it, okay? So it's necessary for it to be there, but I should never try to recover it. And I will show that you don't need to in order to solve the problem that we will solve. Okay, so don't meet your heroes and don't model your latents. All right, so now that's the introduction. So let's introduce proxy variables. So I'm going to do this with an example, which is going to give, I hope, a nice intuition about what's going on. So in this setting, what we are doing is we are giving exercise advice to a population. And first of all, we observe that population over some amount of time. Now, each individual of that population has some underlying state of health, okay? Like that's their underlying health. And depending on how healthy they are and how healthy they feel, they're going to learn, what they're going to choose, a form of exercise. So in this case, treadmill or swimming. And based on their underlying state of health and based on the exercise they've chosen over a month, they're going to get a health outcome. So maybe they run a race in a time that has improved. But true physical status, like unless you're an Olympic athlete who can go on a treadmill with an oxygen mask and get their VO2 max that way, you're probably not going to get a good measurement of the state of fitness, a clean, noise-free measurement of the state of fitness of an individual. But what you might get, similar to the medical example from before, is a noisy, incomplete view of this X, okay? So let's say you have a wearable like a Fitbit or an Apple Watch, okay? So that's going to record a noisy, but still, I think, informative view of the underlying state of health of the people, okay? We've already seen that if we're looking at a causal effect of an intervention, so let's say we're trying to find on average what would happen if we recommended to this population that everybody does swimming, right? We know that seeing W alone is not sufficient, right? We've established that. So we need a bit more information. So how much more information do we need? Well, what if we also see the noisy view of x after the month of activity has happened? Okay, so I have my noisy view of x before the month of activity, and I have my noisy view of x after the month of activity. And it turns out that under some assumptions that we're going to get to, then this noisy view before and the noisy view after the action A are sufficient to recover the causal effect of an intervention. Okay. Yes?
So this, can I roughly understand this, if you're using this extra information, it's not like exactly trying to derive the causal from W to A then to Y, but some kind of using outcome to only care about the causality of A to Y.
Yeah, so we're looking at the causal effect of A and Y, and we don't get to see X, but it's sufficient to identify this causal effect to see the noisy view of X before and after the exercise has been done. Yeah. So for those who are familiar with POMDPs, it's actually somewhat in the line of POMDPs. So if I've got a hidden state X at time t, and then I make an observation at time t, and then I take an action at time t, and I get a reward, which is going to be y at time t, then following this action, I'm also going to get a transition to xt plus 1, which is my hidden state, and then that's going to have an observation t plus 1. So this is another way to understand it. Just in this graph here, I've hidden like all of this sort of detail here, because we don't need that detail in order to do the math that I'm going to do. But if you're familiar with partially observed Markov decision processes, this is that effectively. Any other questions? Yeah. Oops, and I forgot an arrow. This arrow is also present. Yeah. It's slightly annoying as well that like time usually moves from left to right, but here I've got time moving from right to left. But yeah, that's the convention. Okay. This is, I think, a nice illustration of the principle. And using this W and Z under a bunch of assumptions that we're going to get to, we are able to recover the average causal effect here purely from observed data, so purely from W, Z, A, and Y. Okay, that's all we need. We don't need X. Okay. I'm also going to say that it's possible to evaluate policies. So policy is something a little bit more complicated. So rather than saying everybody does swimming, it's like, well, we're going to assign swimming to certain subpopulations and treadmill to some other subpopulations. So this adds some complexity to the presentation, so I'm not going to go into it here, but just be aware that this is one of the things we can do. Okay, so this was an intuitive explanation of the setting that the proxy methods apply to. They actually apply to slightly more general settings. So here I have an illustration of the interactions between variables that satisfy proxy assumptions. And you can see that there are additional interactions that we're allowed to have while this is still valid. For example, X and W can have a hidden common cause. So there could be some V out here, which is influencing both X and W. That's allowed. And same for Z and A. And you can have arrows from W directly to Y. Like all of this is allowed. So in fact, we can have a more complicated graph than the one that I showed on the previous slide. But there are two core assumptions that absolutely need to hold for any of this to work. And these are what we're going to call the structural assumptions. So one is that W is basically bottlenecked from ZA by X. Okay, so W is independent of ZA given X. And Y is bottlenecked from Z by X and A. So basically, yeah, Y is independent of Z given X and A. So I'm going to color code these assumptions so you can follow where they appear throughout the talk. So we've got our orange assumption and our purple assumption. And these assumptions both need to hold in order for anything that I say to work. These are mandatory. So any graph that satisfies these assumptions, we're going to be able to get it to work. Okay, so initially it seems a bit magic because I said I'm not going to model my X and I'm going to see like 2 pieces of noisy information about it. 1 was not enough, 2 is enough. Like it seems a little bit magical. So in the next slides, I'm going to do the complete proof of why it is that proxy methods work, which is actually remarkably short and easy. And once you see it, you're also going to see what other assumptions we need because we're going to produce them as we need them. Okay, so let's start with just the average causal effect if x were observed. And we've seen that already. We have y given x and a, which we marginalize over x. So in this case, x is multinomial, and it has one of dx possible values. So I have a vector of dx values here, and I just do that marginalization. Okay, and then y is also multinomial. It has dy values, so I get a vector of dy when I do that. Okay, so I'm going to use a slightly more concise notation for this, which is using a matrix vector expression for the previous expression. So this is a dy by dx matrix. So for every a, for every treatment, it's a dy by dx matrix. So probability of y given x at that a. Okay, so each a gives me a different matrix. And then this is a dx by 1 vector, which is the probability of each of my possible values of x. So that notation, basically, matrix vector multiplication is marginalization in my notation. So that keeps the math clean for the next slides. Okay, now that's great, but I don't want x in my expression, so my goal is to write an equation with no blue in it. Okay, so now I'm going to introduce one of my two proxies, which is w. All right, now let's say that I could solve the following equation, right? This equation, it basically maps from w given x, okay, which is a dw by dx matrix, because w is also multinomial, to dy by dx matrix here, which is y given x and a. And I have an H matrix here that for every A does that mapping. Okay, so for every A, I have a different H. Now to solve for this H, I need to take the right pseudo-inverse of this W given X, which gives me a new assumption, right? It tells me that dW has to be greater than or equal to dx, and that the rank of this has to be at least dx. So what is that ruling out? That's ruling out, for example, that a given X basically has, well, if let's say two different X's have the same distribution over W, then I'm in trouble. Okay, because I can no longer distinguish them, and that would break this rank assumption. Okay, but that's also pretty intuitive, right? If two different hidden x's give you the same distribution over W, then plainly you're ill-defined. So let's say that that assumption holds. Here is my original average causal effect. I'm going to now substitute in this expression here. Okay, HWA, PW given XPX. This is marginalizing over X. And so now I have an expression for my average causal effect, which does let me integrate over W. Okay, but to do that, I need to compute this H matrix, and to compute the H matrix, I have to have seen X, right? So if I saw X in training, then I could marginalize over W to get my average causal effect. So I'm partway there, but I'm not all the way there. Okay, so let's take this equation and put it on the top of the slide. So this is from the last slide here. Now I'm introducing my final proxy variable, my Z. Okay, and you can see there's a gap here. So what I'm going to do is I'm going to project both sides of this equation onto something. Okay, and what I'm going to project onto is px given z for each a. Okay, so px given za for each a, I get a dx by dz matrix, and I'm projecting both sides onto that same matrix. Okay, I'm multiplying by that matrix. Now, this again gives me a new assumption, right? This thing here has to be of rank at least equal to dx. Otherwise, I'm going to increase my null space, and I'm going to not correctly solve for h, right? So, you know, dz is greater than or equal to dx, and this thing has rank dx. Once that's true, well, now we start using our assumptions. So first of all, the orange assumption. Because of the orange assumption, w is independent of za given x. This here amounts to marginalizing over x, and I get pw given za, which is purely in terms of observed variables, and so I compute it from observed data. All right, what about the other side? Well, y is independent of z given ax. So when I take this matrix product here, I'm marginalizing over x, and I get y given za, which again is purely in terms of observed data. So now I have a system of equations that I can solve for h. I can solve for h, and then I can get my average causal effect by multiplying h by p of w, and I'm done. Okay. So notice that I've at no point recovered the x, right? I know that it needs to exist. I know that its dimension needs to be less than or equal to dx and dz, sorry, and dw. And I know that the rank of this thing has to be dx. But apart from that, there's nothing that I need to do. Okay, any questions so far? Yep.
Then intuitively, that just means, for example, between x and w, w has to be method enough to distinguish how the source of the actual physical status can be distinctively represented in different dimensions of the field.
Yeah. So let's say that X is, healthy or not healthy, right? Healthy should have a different distribution over your heart rate, if W is heart rate, than unhealthy. Unhealthy should have a different distribution over heart rate. So basically, different values of X should have distinguishable distributions over W. So my distribution of my Fitbit data should be different if I'm healthy or not healthy, if X is only 2 dimensions, let's say. Yeah.
But then a similar symmetry also is needed for the relation between Z and X.
Correct.
And then by using both of them, then this doesn't hold.
Yeah, that's right. And then we can recover this. Yeah, exactly. Yeah. Yep.
While I see clearly where the wrong assumption comes from, intuitively, what it means in terms of the definition of probability, it's not obvious.
Which assumption, sorry?
The rank.
The rank, yeah.
The rank.
Yeah. I mean, so basically, it means that like different X's should have different distributions over W. So it's not that I can like recover X uniquely and deterministically from W. It's just that the distribution over the data should be different for different values of little x. And so, it's not that if I'm healthy or not healthy, I'm going to get like exactly this or that distribution over my heart rate. Or rather, exactly this heart rate, but I'll get like a different distribution over my heart rate if I'm healthy versus unhealthy. Yeah. So, it's not that I need a deterministic link. It's just I need a noisy link, but it has to still be a noisy link, which is the noisy W has to be different for different values of X. Yeah. Cool. Okay. So this was all for categorical data. And so now the question becomes, well, in the real world, I've sort of talked about treatments being high dimensional. I've talked about, my W's and Z's being high dimensional. What do I do now in these real world problems? Okay, so this was work by these very talented authors here. So we did it with kernel features. So that's Afsaneh, Yu Chen, Anna, who was here just a little while ago, Limor, Matt Kuzner, Ricardo Silva, and Quick Amal. So we did a kernel paper. Then shortly afterwards, we did it with adaptive neural net features with Liwan and Heishiro. So I'm going to focus in this talk on the adaptive neural net case, because it has some additional interesting properties which are going to be sort of topics for discussion and add a bit of complexity in interesting ways. I should also say that when we're implementing this in the real world, it can be a little bit tricky. So I urge you to use the code that we've provided and save yourselves a lot of pain. So the code is here. Yeah. Okay. So the lucky thing about doing proxy methods is that it's actually very simple because there's only one model and there's only one way to solve it for the rest of the talk. Okay, so here is my one model, and throughout every remaining part of the talk, this is the only model that I'm going to be using, which is that my prediction at some point is a linear combination of neural net features of that input. Now, it's interesting that I'm distinguishing the linear final layer from all of my other neural net features, right? I could just say, like, everything is theta and I've got a neural net and I'm done. But it turns out that separating out the linear final layer is going to be something that is very necessary to us as we get further on in the talk. So that's why this thing is a little bit unexpected. Now, just to contrast with kernel methods, in kernel methods, we would have an infinite linear combination of fixed features. So that's the distinction we're making here. Okay. Now, I said we have one model, and I said we have only one way to fit it. This is the way we're going to fit it. We're going to fit it with ridge regression. Okay? So I have a square loss between my neural net prediction and my outcome. I have this additional ridge term here, which ends up being quite useful to stabilize the method. Now, I've separated out my linear final layer and the rest of the neural net parameters. And what's interesting about having done that is that I can now solve the linear final layer in closed form as a function of the rest of the parameters, right? So, what is my linear final layer? It's just the cross covariance of y and features of x, the covariance of features of x with themselves, plus lambda from the ridge inverted, right? So what I can do is, in fact, I can take this, I can put it in here, and then I can backprop through the Cholesky in order to solve for all of the thetas, but I never explicitly have to compute my gamma here. Okay, so this is a trick that we're going to use. and it's going to be very useful to us. Okay, any questions? Yeah.
If you solve one is just bridge regression, right?
Right.
And I don't see, like, in terms of your gamma hat, why you don't have a linear term in y, but you have a covariance somewhere. Cross covariance in y.
So I have, this cross covariance is between the y, which is a scalar or vector, right, and the features of x. So it's not a covariance between features of y and x. It's just plain y. Yeah. Yeah. Yep.
A quick question. There are reasons why you don't want to learn the gamma and still backpropagate instead of learning it jointly in practice?
Yeah. So you will see actually reasonably soon why it is that I do this trick. Yeah. Like a priori, it's not obvious to do it. We can talk a bit afterwards. Actually, there's some interesting optimization implications, but for this problem we're solving, we have to do this. Yeah. Yeah. Okay, yeah, so I've got this closed form expression, and so effectively, like, the linear final layer is a function of all of the remaining parameters, and so this is what I use, okay? And so, like, you know, gamma is no longer explicitly present, it's just basically a function of theta, which we put in. Okay. And this will become clear why we're doing this later. It's actually a very subtle and interesting reason, so just, like, that's some, foreshadowing for you, okay? So this is how we're going to proceed for the rest of the talk. I introduced the proxy variables when all of my variables were categorical. I'm going to introduce a proxy relation when my variables are continuous. Then I'm going to introduce a loss function. So what is the loss that we minimize in order to get the proxy solution for continuous valued variables? And then it's going to turn out that I need ridge regression twice in order to solve it. So not once, but twice. And we're going to see why it's twice. Okay. And you'll notice the color coding here, which is to remind us of which conditions we're using in order to solve each of those regressions. Okay, so here is our average causal effect. It's called a dose response curve when A is continuous valued. And I've taken my chance of being cured, given my treatment and my covariates, and averaged that over a P of x, okay? Now everything's continuous valued, so this becomes an integral, not a sum. We don't observe x. However, let's say that we've solved the following Fredholm equation, right? And this is saying the expectation of w given az of some function, right? So now it's a function, not a matrix, of w and a is equal to the mean of y given a and z, okay? So the conditional expectation of this function here is equal to y. So this is the sort of continuous valued analog to the matrix equations that we introduced earlier. And what's interesting is that the conditions that we impose are analogous in the continuous domain to the rank conditions that we had earlier. So we're sort of saying that if the conditional mean of f of x given a and z is 0 for all x and a, that amounts to saying that f of x is 0. So it's sort of saying that z is a sufficiently rich view of x. And in the same way, we've got this equation of f of x given a and w, which has the same property. So that's to say that w has to be, let's say, a sufficiently rich view of x. So these are the analogous equations to the rank conditions on, you know, z given x and a, and x given a and z, and w given x that we had earlier. Okay. So any questions about that before I go on? Yeah. So we want to solve this equation for h. It's a Fredholm equation. It's ill-conditioned in practice, so in practice we're going to get a minimum norm solution h for this. Now, this is the equation we want to solve, and notice that x is not observed, nor is it modeled. So this is quite important. I've said that I don't want to try and model or recover my hidden x's, and at no point have I done that. I've just got this equation which maps w given az to y given az. Okay. Once I've solved for this h, just as before, I marginalize over w in order to get my average causal effect. Okay. So I need a loss function which is minimized when this equality is true. because then I can minimize that loss over h, and then I can find the h that has that thing condition, and then once I have that h, I can compute this thing. Okay, so what does that loss look like? Okay, so this is the second step now, where we're getting the loss. Our goal is to get an h that satisfies this relation. I claim that the loss is this. Okay, expectation over y az, y given EW given az of h squared. Why is that? Okay, so let's go to good old least squares regression. Let's say that we are solving least squares regression for some function f, which is a function of a and z, to get y, right? What is the f that minimizes that squared loss? Well, it's the conditional mean of y given az. But guess what? We have the form of y given az here. It's this, okay? So if I take this and plug it in here, then I get this loss, and that's it. So very short answer. All right, we have a loss function. Okay, next, we need a parameterization of our h. And here I'm going to use a very strange parameterization, and then I'll explain to you in the next slides why I did it. Okay, so here is my parameterization of this h function. So what it is, it's a Kronecker product of neural net features of w with parameters theta, and neural net features of a here with these parameters zeta. And I've got basically like this Kronecker product, which amounts to saying the product of all pairs of features. Okay, so it's a big long list of products of pairs of features. So, and then I've got this linear final layer. So, questions come up, right? Why this Kronecker product? Okay, why not just have a neural net that takes in a and w and spits out the prediction? And then why the linear final layer? So I've set up this mystery, so now we're going to explain why, finally. Okay, so I want to solve h that has this relation. Here is my loss. I have added this ridge term here. Okay, now at this, sorry, yeah.
Which is not gamma but h1.
Which is not gamma but hy. Oh yeah, so gamma, I should clarify. Gamma is the linear final layer for hy.
Oh, yes.
So I've just put a ridge on the, yeah, cool. All right, and this is my loss. Now, you know, as I said a couple of slides ago, normally when you do regression, you have a function here. But in this case, we have a conditional expectation of a function. So the input to my squared loss is not the function that I'm trying to solve, it's the conditional mean of that function. And this is a little bit unusual, right? And so it's like, okay, like if I'm trying to solve not, you know, for the function, but the conditional mean of some function, you know, over its arguments, then what on earth am I supposed to do? And so there are some solutions to that, right? One would be to learn a model that generates samples of w given az. So like a given a, obviously you don't have to generate, but w given a you do, right? So I could learn a model. I could learn to generate samples of w given az, and then I could take a sample mean, and then I could do it. Now, that feels like it could be a good idea, but it's also solving a hard problem. So imagine like w is all of the information that you get from a Fitbit in a day. Like that's a very high dimensional distribution. And now I'm saying, okay, generate me all of these, you know, w's given the same super high dimensional thing after a month. Like that's a very hard problem, right? And it seems that it's a harder problem than we need. So rather than solving that hard problem, maybe we could solve an easier problem. Okay, so let's rule out sampling because we think it's going to be too hard when w and z are super high dimensional. And let's do something else. Okay, here is the form of the equation that I got from my previous slide. Okay, and I had this sort of mystery, like I put it in this form for some strange reason. Now I want to take the conditional mean of that thing. Okay, so let's put the conditional mean in here. Now a given a is a, right? So nothing happens. But now what I want to do is I want the conditional mean of this. Now I can take this conditional mean in here, right? Because it's a bilinear form. And so now I have the problem of estimating a conditional mean of a vector of features of w. Now let's say those features are, you know, 10-dimensional, even 100-dimensional. That's still a much, much easier problem regressing to 100 dimensions than trying to generate features in hundreds of thousands of dimensions, or W's in hundreds and thousands of dimension space. Okay, so basically what I've done is I've said, look, in order to solve this problem, if I take this form of my H, then I have a very easy way of taking the conditional expectation, which is to compute the conditional mean of the neural net features of W that I'm using. Okay, now there is, I think, a deeper principle at work here, which is that this is the way that I'm representing the conditional distribution of W given AZ, right? I'm representing it as a vector of conditional expectations of features of W. So elsewhere we've called that the conditional mean embedding, and this is, a representation, a valid representation of a conditional probability. And so this is what we're using here in order to simplify our problem. So any questions about that before I go on? Yep.
So of course, I think according to your suggestion and the principle here, that it simplifies the level of difficulty in computation. But we potentially need to later justify, like either theoretically or empirically, so if this form, in terms of expressiveness in trying to model the underlying true H, can be comparable to if we use a more computationally intensive way.
Yeah. No, so this is a good question because, I've chosen this because it makes my math work. But then, how much representational capacity do I give up? So if I were doing this in kernel land, and if I were using two Gaussian kernels, then I would actually have basically very little lost. So I'd still be dense in the space of continuous functions on W and A together. Now, when I'm using neural nets, I think, there it becomes a bit more of an empirical question. And so, if my neural nets get rich enough, and if I'm able to estimate my function well enough, then I'm probably okay. But at least in certain limiting cases, we know that we are, quite a rich function class. Yeah. Mm-hmm.
What about taking linear combinations of products when rich?
Right. So if you say linear combination, so right now we have basically like a linear combination of all products of pairs of features.
Yeah, but your phi theta 1 and phi theta 1, they are given, right?
So phi theta 1,
yeah.
these are learned neural net functions. Yeah. Yep.
Thanks.
Yeah. Yep.
Suppose if you're using completely kernel approach to solve this problem.
Yep.
Then how would you pose this so in the last layer you don't model with the neural net?
Mm-hmm. Right. So if I'm in an ArcHS, these guys here are fixed, infinite feature dictionaries. I'm still using this Kronecker approach. But now, like the linear final layer is just my if I have my f of x is dot product of f and phi of x, which I can even write down, right? Fx, right? This phi of x in kernel land is fixed, right? It's not an adaptive feature. It's just a vector of ArcHS kernel features. Yeah. But I'm still using this Kronecker representation, and then I use a kernel mean embedding, a kernel conditional mean embedding for my W given ZA.
So basically, you kind of separate the features by looking at this kind of a front, right? Because you don't want to model the features jointly.
Yeah, absolutely. Because W given ZA is a conditional mean, but A given A is a identity operator, right? An identity operator is not an ArcHS. So yeah, you want to basically decouple them. Yeah. Any other questions?
So just a remark, Yasno. So you started from the kernel version, and then you extend it. This is very natural.
Yeah, exactly.
Kernel point of view.
Yeah. So this is why kernels are useful. Yeah. Everyone should start with kernels. So this is how it's totally how we arrived at this, basically. And in fact, this now comes to the reason of why I chose to present this with neural nets, which is that when you use neural nets, there's one additional point of complexity, which is now going to arrive. Before I get to that point, first of all, to get the conditional mean of features of W given AZ, I solved that using ridge regression once again, But it's now ridge regression where the output is not a scalar, it's a vector. And so the mapping from my features to my output, which I get with ridge regression, is now a matrix, right? Rather than being a vector. So I said there's only one algorithm in this talk, it's ridge regression. How do we solve F? We solve F with ridge regression. Okay, so let's go into a little more detail. Okay, so this is the ridge regression solution we solve, which in kernel land is called a conditional mean embedding. Let's write this down and basically work our way through it. Okay, so I want a matrix F that takes my function, my features of AZ, which have a parameter here, and gives me my conditional mean of functions of W given AZ. Okay, now notice here that I haven't decoupled my features of A and Z. I've just got a single neural net that ingests A and Z and puts out a vector of features. Okay, how do I solve it? I solve it with ridge regression, where this is basically like, you know, a trace of F transpose F, that's my ridge term. And then I've got a squared loss here, which maps my features of AZ to features of W. Okay, now, as we did earlier, right, I don't have explicitly this F, I have it implicitly as a function of theta and zeta. Actually, that's my zeta, my other one was psi. Yeah, so I have F as a function of theta and zeta, and then I can backprop through Cholesky in order to minimize my input features of my regression and to solve for those. Okay, so this is giving me a good estimate of my conditional mean of features of W given Z. Okay, so I said that I backprop through Cholesky for zeta, but not theta, right? So that's interesting, like why not, right? And in fact, why not in retrospect is very obvious. Theta is a parameter of the output of my regression, okay? So let's say that I learn a theta that makes this a vector of zeros by backpropping through Cholesky with F and solving for theta. Well, that's a very easy regression to do. And then my F becomes a vector of zeros as well, and I've solved it, I've got zero error, everything is fine. But this is not very useful for the downstream task, okay? And so basically what that means is that I need to fix my theta features for this phase of the problem. So I'm able to optimize over my zeta and my F, but I'm not able to optimize over my thetas. Any questions about that?
Then you do alternate.
Yep, so we get to that, okay? So now here is our final algorithm. So first of all, we solve for f hat, which is a function of theta and zeta, and then we backprop through the Cholesky to optimize the zeta, which is the stage 1 features. So then in stage 2, I solve for gamma in terms of f times this, right? So gamma is known in closed form in terms of that. Now theta is the input to the green regression. And so I can backprop through for theta, my stage 2 loss, okay? So basically, if I go back a little bit, this loss here, I'm able to backprop through for theta, okay? Now, the beauty of doing that is that my f actually, as I change my theta, this f adapts, so it remains a correct conditional mean. And so this finally gets to the point of, you know, why did I have this separate linear final layer? I have this separate linear final layer so that I can do this trick, which is to say that as I adjust my theta, as I adjust my neural net parameters of my second stage regression, my first stage regression continues to be a correct conditional mean of those features. And that's because this f is a function of those thetas. So this is quite important, so I will pause here. Yeah. So basically, like, you know, I have a conditional mean of features of theta. I want, as I adjust my theta, that remains a conditional mean. And doing what I just described ensures that that is true. Yep.
You can, I have the, if you backprop through Cholesky,
yep,
then you cannot do mini batches.
So that is a very subtle and good question, right? So when you backprop through Cholesky, it's sort of like doing coordinate descent, where you give, like, you know, you effectively take all the steps in your linear final layer, but just small numbers of steps in your remaining parameters. Does what I say just now make sense to you? So, like, I solve for gamma in closed form as a function of theta. That's sort of saying that I take all of the gradient steps on gamma. I solve for the, like, global solution of gamma on that mini batch. Does that make sense? Not so much, yeah. Yeah. So
two other questions.
yeah. No, so it's a very good question. So like one question that you have if you're doing the linear final layer in closed form is it stable when you do non-mini matches? And the answer is yes, with some tricks. But I did not talk about the tricks, but you spotted that tricks would be needed. Yeah. And so, in practice, you don't necessarily, you have some like prox term with respect to your previous solutions. So yeah, and this is how you make it run.
You have an iterative way to update.
Yeah. So this is. I mean, in practice, in our initial implementation, we didn't use it, but as we have developed further, we have found that this helps. Yeah. I think the current one online doesn't use it, and it still works pretty well. But you can make it work better using these tricks. Yeah. But yeah, we use slightly larger mini batches in our initial implementation, so that's the way we do it. Yeah. Yeah. So that was yeah. But yeah, let's say the main requirement, which is basically like to have the two stages sort of communicating between each other, like this is necessary. Like if you don't do that, then it doesn't work. And so this f has to be explicitly a function of theta, so that when you adjust your theta, it doesn't sort of like drift the solution too far, or the conditional mean. Yeah, the conditional mean still remains correct. Yeah. Okay, any other questions? Okay. So yeah, so this is how we do it. And then coming back to Florence's question, we do in fact iterate between our first and second stages. So basically, like we alternate between optimizing our second stage and our first stage regression parameters. We iterate until convergence, and then we're done. Yeah. But yeah, the main sort of thing is that okay, the conditional feature mean is a little bit suboptimal in stage one, but it does remain a correct conditional feature mean because of the trick that we did. Okay. Some very good questions. Yeah. And so this is kind of interesting because the features that we learn are features that, are basically, on one hand, good for, in respect of getting conditional means, and on the other hand, good at predicting y. So there's sort of features that, the stage 1 and stage 2 regression sort of cooperate in order to learn these features of w that are easy to predict from z and a, and that are predictive of y. So they're kind of features that are sort of good for the problem that you're trying to solve. Which is very useful because, going back to the earlier suggestion, like if we tried to generate samples of w given az, like this would be a really hard problem. But instead, we're learning conditional means of features of w given az, where we've learned that we've learned these features in order to sort of make, computing the conditional mean of these features easy, and yet having these features good at predicting y. So they're kind of the best features for the problem we want. This is an additional, I think, complexity over using kernel features, because in kernel features, they're fixed, like you're given the features and you're done. Now you have to learn the features, and you have to learn the features to sort of trade off predictability and predictivity. So they have to be predictable from ZA, and they have to be predictive of Y. Yep. Oh, yeah. Okay, I thought that was a question. Yeah. Yep.
Just trying to defend kernels in the sense that what you're doing is a kind of finite rank kernel.
It's
a finite rank kernel.
Yeah, it is a finite rank kernel with adaptive features.
Very subtle way of including information in.
Yeah. No, that is fair. Yeah. I should also say that there's this very nice paper on bilevel optimization by Petrolionnet, Meral, and Arnel recently. In fact, it appeared in Europe last year. They have a very clever bilevel optimization method, which is, I think, a better way of solving the problem that I just described than the way that we've done it. And it's certainly much more mathematically grounded. So this was a sort of a machine learning solution, but they have done it properly. So please read that paper. Okay, so I can talk briefly about some experiments. So these are synthetic experiments, so it's not super exciting, but I can still describe it. So basically what we wanted is to demonstrate an example where the where the treatment was high dimensional. And so in this case, X is something fairly low dimensional. It's the scale, rotation, and position of some sprite. But then the treatment is in fact the sprite generated with those parameters. So the treatment is now an image, it's high dimensional. And the y is a scalar, but it's a complicated function of this image with multiplicative confounding. by an element of x, because there's a link from x to y, then z is basically a noisy view of x, just in fairly low dimension, and then y is, w, I should say, is an image with a noisy version of some of the parameters of x, okay? But the sort of key point here is that in this example, both a and w are image valued. So they're very high dimensional, and it matters to learn neural net features for this setting. So we're comparing against two classes of methods. One is a kernel set of methods with just the classical Gaussian kernels, and the other is something called CEVAE. So what that does is it's doing what I said not to do, which is that it's learning using an autoencoder a latent representation of x, okay, given everything that it's observed, so the d, the w, and the a, and the y, okay? So it learns this latent representation, and it uses that, the latent state of the autoencoder as if it were x, and then it just does what it thinks is best and sees what happens. So the argument against doing that is that the latent space of the autoencoder is sort of information necessary to reconstruct what's observed. But that isn't necessarily like the context information you need for causal effects. So if W is super high dimensional, there might be a lot of junk in W that really doesn't matter. But the latent space of the autoencoder still has to be rich enough to reconstruct it. When that's the case, it's not very good when you're doing causal effect estimation because it's got too much junk in there. Yeah. So that's a sort of intuition as to why the autoencoder approach didn't work so well. And so you can see that in practice as well. So here, basically, the CEVAE approach for this example didn't work super well, whereas the neural net methods are working best for this example. Yeah. So we have also a example for policy evaluation. So in this case, this is a synthetic demand data set. So basically, it's a synthetic data set to predict the effect on demand for airline tickets of adjusting the price. A is the ticket price. And basically, we've sort of set it up that Z is the price of fuel. It's a noisy proxy for something, I forget what. And the policy depends on that. Okay, so here what we're doing is we've gathered data under one policy, which is whatever policy was used in generating the data. But then we're saying, okay, if price is a certain function of fuel cost, then what would happen in future? So now A is no longer a point intervention, but it's a distributional intervention. Okay, so A has some distribution given the price of fuel. And in this case, again, we're actually doing pretty well. We're comparing here against kernel methods because the CEVAE approach doesn't apply to this setting. So yeah. Okay, so just to conclude, we can do causal effect estimation with an unobserved x, where there is all sorts of interactions between x, a, and y. We need noisy information about x. Having W on its own is not enough. We need both W and Z, a noisy proxy, and the intuition I gave is that W can be thought of as a noisy view of x before some treatment occurs, and Z can be thought of as a noisy view of x after the treatment has occurred. We've, of course, made some strong assumptions about W, so W has to be separated from these guys by x, and Y has to be separated from Z by these guys in order for everything to work. The key messages is don't model your latents, so it's important that they're there, but you shouldn't try to recover them. The other thing is don't try to generate samples of W. It might be super high dimensional, but actually all you need is the mean of the features of W that are necessary to solve your problem, and that's all you need, not more than that. Yeah. So this work was supported by Gatsby and Google DeepMind, and I'm happy to take questions. So, thank you.
Just a quick question, you might be a silly question, but just wondering, in the causal literature, it's quite hard to get the average treatment effects, individualized treatment effects. So in this method, in terms of talking about the policy implementation, can you get the individual and the average treatment effects based on this method?
Right, so the example that we were giving here was indeed the average treatment effect, because this is, on average, right, this is what we are computing, right? We are computing the average treatment effect in the case of hidden confounding. Now, individualized treatment effect would be tricky, right? Because what I would be saying is, like, for some value of x, what would be my causal effect? But the trouble is I never get to see x. And so then, ITE, at least from what we've done here, we can't do. What we can do, though, which is, again, it's notationally cumbersome, but mathematically easy, is I can have, if I wanted to do some individualized treatment effect, I can have an additional W here, okay? And this W is basically something that I observe that I want to condition on. If I have that, then I can. So, obviously X is doing whatever it does, but this W that I do observe, I can then say, okay, what would happen if I did this treatment for people whose W had this value? This I can do. Yeah.
Thank you.
Yeah. Mm-hmm.
Theoretically, what can you think can be shown? Or what questions can be asked?
That is a very good and challenging question. So, and it's going to have a slightly long answer, okay? The challenge is the following. Let me just go to it. Here it is. Okay. Here is our regression. And the problem is that I've got here a that passes through. So, I've got E of W given AZ of a function of A. So A passes through, okay? But then W is a conditional mean of W given AZ. So that gets squashed in some sense. So the problem, I think, if I didn't have this A, if A wasn't here, then I can basically say at this point, I know how to get minimax rates. The moment that A is here, we have a gap between the lower and upper bounds, which we have not been able to close. And it's for very interesting reasons, and we are not sure how to get around that problem. Yeah, and it's basically because you've got a function of two variables, one of which is being squashed by the conditional mean and the other of which is not. And so it basically becomes very, very troublesome. Yeah.
I have a question.
Yep.
Do you have some application test cases with wearable data that you can talk about?
So in the proxy setting, so I think let's say the reason that I gave this health example is because this is sort of, let's say, related to the kinds of problems that I'm interested in, which is, that you've got basically, like, you've logged a bunch of data from people acting according to their own internal state, and then you're saying, look, if I gave this population some fitness recommendation, what do I think would happen? And so, things like that would then allow me to sort of make a recommendation, like, how about doing this kind of exercise for the next period? Yeah. So I think that, to me, is the sort of nicest illustration of an example along these lines. Yeah. Yeah. Mm-hmm.
So in regard to the previous question, so you said you have upper and lower bounds.
Mm-hmm.
You're minimizing on HY, right? So it remind me that HY, you assume to get this bound, you assume HY is in like RKHS or like it's a neural network function.
Right. So we have not yet attempted this for neural nets. So this is just for RKHS. So H, we're going to even be well specified. So H is in its RKHS. Yeah. And what you want, in fact, is to get the, recover in L2 norm the difference between my true H and my fake H. One of the challenges is that you're recovering something in L2 norm, but the loss you're minimizing is a conditional mean. So there is going to be like some sort of gap between the loss that you're minimizing and the answer that you want it to hit. Now, if A wasn't there, we know how to do it. And there's a sort of measure of basically how well specified the problem is, which then enters into the bound. When there is also this A, then you're kind of compressing the function in the W dimension, but you're not compressing it in the A dimension, and that messes everything up for us. Yeah. Yep. or maybe 2 questions. It's okay. So last
No,
day.
it's
Yeah.
more general.
Okay.
Do you want
No,
Yeah.
it's not technical. I just wanted to share with you some results. Don't you think that kernel method is kind of a prototype method? So when you think with RKHSs, you can define easily a prototype of your solution. And if you go for more expressivity, you go to your method. And maybe what I'm saying is obvious, but I think that there is 2 parts in your reasoning, 2 key ingredients. The first is, well, this idea of X and Z and W, of course, but after diffuse treatment, but also the fact that you have thought in terms of RKHSs helps you to see where
I
mean embeddings, and then you.
No, I really think so. I think that like the way that we did this, so there was an earlier paper on instrumental variable regression, which is a sort of another way to do like causal effect estimation with hidden confounding. And yeah, that we did the same thing. We did it first with kernels, and we said, okay, like with fixed feature dictionaries, what does this look like? And it's really useful because it's one less moving part. You can sort of figure out what everything will look like, and then you say, okay, now what happens if I start moving my features? And then then you need some additional tricks like this optimization trick that we talked about. But it's sort of you're right that the way that we thought about it was really like it was very helpful to have the kernel frame for that. Yeah.
And it still could be true if you use deep kernels. If you use
like kernels on neural net features. So I think though it's just somehow like it's very handy. You just say, look, I've got a feature dictionary. What do I do? And then I do that, and then I say, okay, now what happens if I can remove my feature dictionary? What happens? And so I can
Thanks. So you mentioned the sharing some interesting coincidence of ideas with PUMDP. Is there really some work there with this kind of approach, or do you think there's a promising way to extend both the mathematical insight of simplification, factoring out, and the corresponding, say, bi-level procedure of optimization back into the, say, off-policy evaluation in PUMDP settings?
Yeah, no, I think that's a really good direction to do.
Given this side.
So I think the original paper that noticed the link with PUMDPs came out in 21, and we cited, of course, in our paper. But I think there's like lots and lots and lots of space to do work in that direction for sure.
Especially given, say, robust or more explicit understanding of different policies that one can ever choose from the space of policies.
No, I think there's a lot of nice work to be done in that direction for sure. I mean, there's other things as well, like there's like confidence intervals. So we're hopefully going to submit to NeurIPS like a doubly robust version of this. So that's another thing that one can do, which is and one can then do crossfitting to get error bounds. And so like there's a few different things that one can do to extend this. But I think there's a lot of space actually to do work in this area.
Thank you so much.